So, let us come to the introduction of iron making. As I am not sure how many of you are aware of it, but in a human body we have about 4 gram of iron, which means iron essentially is a part of all living things. So, it is very important in our life, and as such iron as an element was forced by nucleosynthesis in all the nuclear furnaces of the stars. So, if you read about the evolution of the stars, you will come to know iron is formed by nucleosynthesis process, and history tells that iron was first produced from meteoroids and then to iron ore. And in fact, the name of iron comes, some say it is like a holy metal, and it is also in the old age they say the metal fall from sky. So, the first evidence is iron came in the form of meteoroids, so fell from sky, and that is how they gave the name iron. If we look at the percentage of iron in our earth, so it is about 35%, which is a very big amount, and but most of it is concentrated at the core of the earth at the center, and it is inaccessible. So, we cannot reach due to very high temperature at the center. So, whatever is available belongs to the earth's crust, and that is the iron which we are using at present, and this is about 5% of earth crust. And some of the iron ores is hematite, magnetite, which are shown here. So, beginning of the metal smelting, as you know, it started in Neolithic age, and earlier evidence of exploiting metals like wheats of malachite and copper about 7250 BCE. So, in fact, the Iron Age came quite late. First the Stone Age, then Copper Age, Bronze, and then the Iron Age. So, iron has remained at the core of the civilization for around 3000 years. The oldest known ferrous alloy production was about 2000 BC, and probably it is maybe more than sometime 2000, it is about 3000 actually in India. It is a written one. So, that definitely we can say in India it was about 3000 BC, and the boots is still one of the main important iron process known is Boots steel of India, which was used in making Damascus sword and exported worldwide about 2 million ago. And this is the Damascus wood steel sword which went all over the world. And then another one we have around 1550 years old, known as iron pillar in Delhi, which is not rusted yet and quite heavy. This is another marvelous of Indian metallurgist. So, once this slowly after getting into this Iron Age, it spread wide to wide geographic area by 1350 to 1100 BC, and evolution of technology in Europe and Asia have different timeline, which is a clear example of how development responds to local condition, both geographic and economic. If you look at the history more closely, you will find these are very different timeline for Europe and Asia. So, it is difficult to say what has happened in Europe is true all over the world, and same thing is about the Asia. So, it is a human settlement where it has occurred, this technology developed. So, iron was produced by reduction of its oxides or hematite, magnetite, geothite, siderite, etc., and where human settlement had occurred, as I said in the previous one, and reducing agent was carbon and various form of wood or charcoal. The feeling is when the human was settled somewhere and they were probably burning the fire, and the earth or that place was iron rich, they found sort of a nugget or some hard material, and that is how this iron was discovered and this it started used. So, the first process to make steel was direct reduction process that produced unalloyed mild steel, and modern iron making still uses this 3000-year-old process known as the carbothermic reduction, because carbon is the main reductant here, and that is how it is known as carbothermic reduction. The way it started and what we know, it is in sort of a bloom used to produce, and that place used to call bloomery. So, in that one it used to have a bowl shaped clay hearth of knee high, and that one temperature, so it is something like that, and they are blowing the air through this into this pot, which is temperature is about below 1450 Kelvin. So, that is below the melting point of iron, but it was high enough to reduce its oxide. However, this spongy product which you get after reduction of oxide is not pure, and that is why it is known as bloom, consisting of iron, slag and some impurities. With the actually this video could show you a little, can give you a little idea about can we stop? So, this spongy product known as bloom was consisting of iron, slag and some impurities. The following movie gives you an idea about how the blooms are produced. So, with the process of so you saw this movie which shows about the spongy production of bloom in the old age, but you know as the time passed, demand of this metal increases due to its hardness and other properties. So, with the passage of time and more demand, high bloomers came into existence up to 0.5 meter high, as you can see in in this figure. Of course, this is higher than that. So, more and more higher bloomers came. So, iron can only be separated from slag completely when both are in liquid state. So, as we were saying, when the demand is more, then production should get increased. The mechanization of the thing came, as you can see in this one, the blowing is through the water, and so this is mostly what you are seeing is about the art of iron making. As the people wanted more and more things, so they try little innovative idea and started increasing the size of the bloomers and more production of the bloom. But with the increase of the demand, I think that art was not sufficient to fulfill it. So, slowly science and technology came into picture, and the first use of coke was happened, which because as you go high, coal or charcoal or wood does not have that sort of strength which can withstand the pressure of the material. So, they were restricted to it. So, invention of the coke came through the coal. Then use of air blast, because if bloom becomes high, you need more and more air, and with the invention of steam engine, high power blower were available, and that is how the air blast came into picture in iron making. And to increase the efficiency, then preheating of the air blast started somewhere in 1829, and it is found that lots of heat is going waste in the form of exhaust gases. So, utilization of that also started somewhere in 1845. So, essentially iron making what we have today is about 600-year old process. It is a part of the extractive metallurgy, which is classified into three types: pyro, hydro and electrometallurgy. And pyrometallurgy is related to the heat, and this is the oldest branch of extractive metallurgy, and iron making actually comes or falls under this branch, pyrometallurgy. Now, coming to the modern iron making, not exactly, but if we see the development of modern iron and steel making, then this is around only 3 quarter century old. So, about 7 or 8 decades. So, pyrometallurgy is the oldest branch of extractive metallurgy, and iron making falls under pyrometallurgy. Now, the modern iron making, I will show you one video, a small clip which will tell you about how the iron is produced nowadays. This is the video. So, this clip showed you some idea about the modern iron making, and this is around 7 to 8 decade old, and as the demand is increasing, or the this one new and new technology is coming into this, and due to the economy many of the technology has been changed, and now economy is not the only thing, environmental problems are there. So, many changes have occurred, and as you can see from this slide that you have now, burden, it has to be size, weight, moisture control, all top gas analysis, or skin flow thermocouple, many types of probe, and injection of the hot blast with fuel like pulverized coal injection, plastic, oil, and there are so many things in the blast furnace which is shown in these figures. So, nowadays blast furnace is quite sophisticated. So, essentially if you look at the whole history of it, what we see is going from bloomery to high bloomers to mini blast furnace to the blast furnace, and as you know, due to the environmental problem and scarcity of the high quality coal, people are going back to mini blast furnace and even to DRI, which is like your Bloom's sponge iron, and then using this one into the electric arc furnace to make the steel. So, bypassing the blast furnace. So, do not know after that what it would be, but it looks we are going in a cycle, and if you look at in another way, the reduction technology also seems to going in a cycle from solid state as the bloom, then to liquid state, we are coming to the blast furnace, liquid iron and slag, and again is going to the solid state to DRI, and then using electric arc furnaces or other devices to make the steel. So, it seems again it is going in a cycle, and I will give you a little idea about the modern blast furnace various zones, what is happening in it. So, this figure shows about the physical chemical description of the blast furnace. So, from the top we introduce raw material where iron ore and coke is charged. Now, iron ore depends, if it is just a lumpy iron ore, then it is followed with flux, otherwise it could be only sinter or pellets followed by coke, and this is a tube which distribute this material across the cross sectional of this blast furnace, and where you have a layer of iron ore and coke. Side of this is protected by refractory bricks, and then the steel cell, and cooling is done all around this, and the hot air is goes through these nozzle pipes called tuyere, and a big cavity is formed called raceway, because the coke is racing around here, and this that produce CO, which is highly reducing gas, and that gas goes up and reduce this charge, especially the iron ore, which is coming down from the top. So, slowly this hematite to magnetite to iron ore it get reduces, and when it comes somewhere over here, it becomes semi molten in stage. So, sometimes you call this zone as a cohesive zone. So, either it is a V shaped zone or a W. So, this one is a W and this one is a inverted V shaped zone, and after that the whatever metal and slag is there, it is in the liquid form and only solid coke is there. And so, this is a very hot zone. So, water cooling and other is required in fact across all of these around the furnace, and this is known as Bastille pipe. Hot air is blown through this and your liquid iron and slag trickle down through this, and there is a sort of a lump of the coke. I would say what we call it dead man, because as such it does not take any part in the reaction or any other thing, but it supplies mechanical strength to the burden. And from the bottom you take out this liquid slag and iron from the respective notch. So, this is a brief description of the modern blast furnace, and nowadays they are quite automated, and you would be surprised that the maximum capacity at the moment is 17,000 ton per day. That is a very high capacity, and I am not sure when I am talking to you at this time another blast furnace might have come with probably 18,000 ton per day or something. So, imagine it started with only few ton per day to 500 to 1000 and now to the 17,000 ton per day. So, how much progress has been made in iron making, and the below picture shows all automation and control of the blast furnace. So, mostly you measure various parameters, top case, composition, temperature at various places in the blast furnace, a cooling system, permeability of the bed, and all these are fed, and if there is any discrepancies or not falling under a certain range, the value corrective measure is taken, and that is how the whole blast furnace is controlled now through computers. Very few people work at the at the plant. So, this is sort of a automation of this, and just to give you an idea about the demand of liquid metal. As you can see in 2015 actually this world production went up to almost 1200 million ton, and after the 2013 or 14 it is decreased a little bit, and now it is almost constant. This downward trend is due to because the all data are not available, but if you go to 2016 it is something somewhere here. So, which is almost becoming a constant. And but if you look at this is the world production, the China, it is due to the China which has produced so much hot metal due to their infrastructure development, and now they are reducing their capacity, and India is coming up, and India might be in another 5 years it would be going up to 300 million or another 10 years actually up to 300 million ton. So, India need more infrastructure now. So, India is going up, China is becoming steady and other countries are okay. So, it seems the production would be steady if not decreasing. And the second figure shows how the iron demand of iron has increased over couple of centuries. So, you can see there are three metals which the demand of which has increased quite dramatically. One is nickel, you can see almost 3 magnitude order it has increased in last century. Iron of course, about 2 magnitude order it has increased. Cobalt at the same time almost 3 magnitude, but now it is becoming steady or little bit at the decline side, but iron is still continuing. So, still it has a demand and lots of infrastructure in various countries are getting built. So, this demand of iron will not decrease in near future.